Okay, so today will be the last lecture about data analytics, okay, but not the last lecture for the whole course, okay? So next week, you still have one more lecture with Annie. So today we are going to talk about social network analysis, okay, and specifically applied for fraud detection. Okay, sorry. Okay, so let's talk about some basic concepts. So first of all, so this is actually about the basic assumption about social network. Okay, so that is a guilt by association. So it simply means that, okay, assuming that, you know, someone, okay, is guilty of a crime, okay, because that person is associated with someone else who are involved in a crime. Okay, so in Chinese is 物以類聚. In English, it is birds of the same feathers flock together. So the example is, so say for example, if Tom's best friends, okay, are criminals, so Tom is likely to be involved in the same or similar criminal acts. Of course, you might disagree with such an assumption, okay, because you may be thinking, okay, maybe I got friends, okay, who committed crime, but that doesn't mean that I am a criminal, okay, right? Okay, but then for social network analysis, this is the very basic assumption, okay? So don't come back to me, okay, and then argue with me, okay, why we are performing such a, you know, network analysis, because this is the assumption, okay? So my advice is, if you don't believe in such an assumption, or if this assumption is not convincing enough for you, then don't use social network analysis. Okay, so that is my advice. Okay, so I think again, that is the very basic assumption underlying social network analytics. So again, just some background. Okay, so the following slides are a bit about network problem. Okay, not very specifically about fraud detection. So there is something called the traveling salesman problem. Okay, so I think most of you comes from the computer science background, but I'm not quite sure, you know, whether you're familiar with this network problem. So this is actually a network problem. So what is the problem? The problem is trying to find the shortest path between a starting point and an end point. And the constraint is that, okay, so going from the starting point to the end point, you must go through every other point, okay, between these 2 points. Okay, but then you got to find the shortest path. Okay, so that is the what we call the traveling salesman problem. So I think that this is quite a you know, famous mathematical problem. Okay, that need to be solved. Okay, so this is one example of the network problem. I think that the other one, this one is more interesting and maybe more, in a way, more related to our daily lives, is the 6 degrees of separation. Okay, I'm not quite sure whether you have heard about it before. Okay, so the 6 degree separation, okay, it simply means that any random strangers in the real world, okay, so actually you are being connected. Okay, so in between these 2 random strangers, okay, so the average path length is 6 hops. Okay, what does this mean? So that means every 2 strangers, they could be linked, okay, by 6 hops. Okay, so I think Milgram back in 1967, he conducted a small world experiment. Actually, I have to confess, I didn't really look up the details, okay? But from what I remember, the experiment is like this, okay? So he tried to send out a letter to one randomly, okay, to one of his friends, And then he asked his friend again to randomly send out the letter to one of his friends, so on and so forth. And then he found that after 6 hops, he get back the letter. Okay, so I think that in a way that is a very interesting experiment. Okay, so this is what in real world. Okay, so that means in real world, the average hop of every 2 random stranger is 6 hops. Okay, but then because now you know everyone is being connected on the social network. Okay, like the Instagram, the Facebook, okay, Twitter, etc. Okay, and then some researchers, they found that on the social network, actually the average path length is shorter. Okay, so in real life it's 6 hops, but on the social network actually is only 4 hops. Okay, between any 2 randomly selected people. So I think for us, we are more interested in how we are going to apply social network analytics to fraud analysis. Okay, I think and then one of the reasons why we would like to apply social network analysis is that because there are some limitations if we use the traditional fraud detection models. So you all know that for the fraud detection models, basically for what we have studied, we are more focused on the classification. Okay, so that means, for example, the classification of whether a new transaction or some people, we could classify them as having some fraudulent acts. Okay, but then we cannot detect any relationships, okay, or associations among them. Okay, so that's why we would like to study. Okay, so in addition, so usually for me, I think for the social network analysis is a supplementary technique. Okay, a supplementary technique. Okay, so it's not either or. Okay, so usually it will be a combination of different techniques. Okay, for the fraud detection. So here are just some examples. Okay, where you can employ the social network analytics. So say, for example, for insurance fraud. Okay, so you might find that there may be a number of suspicious claims, okay, with the same group of witness, claimers, maybe even police officers, okay, etc. And then for the bankruptcies of companies, so usually you may see there are some companies with the same group of shareholders, employers, directors, okay, etc. They are opening companies again and again, and then these companies, and then went bankrupt. Okay, and I think for the opinion frauds, okay, very easy to understand. You might have a group of people. Okay, so usually, say for example, giving very good review, okay, to a company or to the products. Okay, so so that's why sometimes we would like to, so in addition to just classifying, okay, for the classification, whether we got some fraudulent cases or fraudulent persons, okay, we would also like to see whether there is any relationships, okay, among the people. So again, some basic concepts before we go into the details of network analysis. So these are the basic concepts underlying network components. Okay, so you can see that for a network, okay, so we will say that this is a graph. Okay, so these come from the graph theory. The mathematical representation, okay, will be like this. Okay, so a graph, okay, would be represented by vertex, okay, a group of vertex and a group of edges. So vertex are actually the nooks, okay, in the graph, okay, are the nooks in the graph. So these nooks, okay, these could be representative of real world objects like people, okay, events, companies, okay, any entities, okay, that you think might be involved, okay, for your study, okay. And then the edges. So usually the edges here connecting nodes, okay, will be the relationship or the association between the nodes. Okay, so these, okay, say for example, if this is an email network, so the edges may be the communication, okay, between two people. And the type of graph, we could have directed graph and undirected graph. So for undirected graph, it simply means there is no direction. And then for directed graph, there is direction, okay? There are directions for the edges, okay? And so the directions can be, can mean different things, okay, if you got different networks. So say, for example, if this represents a credit card transactions, okay, if this is credit card transactions, so these may be the payment, okay, so coming from one person, okay, say, for example, to the merchants, okay. So these are directed graph and undirected graph. And there are, for the edge representation, we can have basically three types. So the first type is what we call the self-edge. So the self-edge simply means the edges goes from goes to itself again. Okay, so like this. Okay, so the example is, say for example, a person is trying to transfer money to his or her own account. Okay, so that is a self-edge. Okay, multiple edge, it simply means that there are multiple relationships or multiple transactions, okay, between two nodes. Okay, and again, the example is like this. For example, in a credit card transaction network, okay, so this might be representing a person spending multiple times, okay, buying things from the same merchant, for example. But of course, I think that sometimes, usually in the graph, so instead of using multiple edges, you may just simply use one edge, okay, and then put a number, okay, to represent the number of transactions. So finally is the hyper edge. So hyper edge simply means, so instead of connecting only two nodes, okay, you are connecting more than two nodes, okay, like this, okay. So say for example, these three persons are, you know, involved in the same events, okay, so then you can use you know, this kind of representation. So for the graph, it could be unweighted or weighted, okay. So for the weighted graph, okay, so for weighted graph simply means that each of the edge, okay, will have a weight, okay, and the weight will be represented by a number. So that number could be a binary weight. So binary weight will be 0 or 1, okay, or you can have negative value, okay, that means negative, 0 or 1. So usually 0 simply means absence of relation, okay, and then you can have a numeric number. So usually the higher the number, so represents a closer affinity between the two nodes, okay. As I have mentioned earlier, actually you can simply use one edge to represent the relation, and then you put number 2 here, for example, okay. So this is the numeric weight. So finally, it's a normalized weight. So normalized weight, the idea is very similar to what we have mentioned when we are talking about supervised learning model. So basically, you scaled, okay, all the weights of the edges in the graph. Okay, so that is a normalization technique. Okay, so finally, the final weight of the edges is the Jiccard weight. Okay, so basically it is trying to measure how social, okay, these nodes are. Okay, so the definition is like this. So actually it is trying to measure the common events, okay, attended by two of the nodes. So V1 and V2. So the weight is calculated by between V1 and V2 is so this is the intersection. So this is the intersection of V1 and V2, okay, and then this is the union, okay, so this is the union of V1 and V2, Okay, so say for example, you got a person A who attended 10 events, and then you got person B attended 5 events, and both of them went to 3 common events. Okay, so then the weights here simply equals to, so 3 is the intersection. So the intersection is the 3 common events. Okay, and then the union. Okay, the union here, it will be simply the total number of events attended by both, and then minus the common events. So this is the union. Okay, so finally, the weight is 1/4. Okay, so this is how you calculate the JCAT events, the JCAT weights. Okay, so and for the because we are interested in studying fraud using the network. So when we are trying to studying the fraud in the network, so we will try to label, actually, we'll try to label the NOCs. Okay, so say for example, we already know about A and B are what we call the fraudulent NOCs. Okay, so they may be involved in some kind of frauds before, so we label them as fraudulent NOCs. So all the other NOCs are what we call the legitimate NOCs, okay, or non-fraudulent NOCs. Okay, so basically, when we try to study these kind of network, okay, so of course we will study the network properties, but what we are interested would be more about the legitimate NOCs, okay, because in this case we already know about who are the fraudulent NOCs already. Okay, so what we would like to know is whether the other legitimate NOCs here, okay, would be influenced by the fraudulent NOCs. Okay, so I think that this is the actually the objective of studying the social network. So on the other hand, there is also one more definition, the EagleNet. Okay, so EagleNet simply means, okay, so say for example, when we look at NOC C, so the EagleNet is would be consisted of A, C, and E. Okay, because we are only interested in one hop neighbors. Okay, we only, because say for example, C to A is one hop, C to E is one hop, but C still can is still connected to F, but through 2 hops. Okay, like this. Okay, so but I think most of the time we are more interested in the one hop neighbor. Okay, because usually for those neighbors within one hop, the influence will be higher. Okay, so again, that is the assumption of the social network. So this is the EagleNet. So about network representation, there are 2 ways to represent network. So graphically or mathematically. So graphically would be, simply something like this. So mathematically, we can use an adjacency matrix or adjacency list. So for the adjacency matrix, okay, so usually it will be an n times n. So the matrix size will be n times n. Okay, so n equals to the number of NOCs in the network. Okay, it will be something like this. Okay, so this is the adjacency matrix. So assuming that, so forget about the numbers here. Okay, so assuming that this is an unweighted graph. So this is an unweighted graph. So the representation in the adjacency matrix is very simple. So when there is no relation, okay, when there is no relation, the value will be 0. Okay, so when there is a relation between the 2 NOCs, the value is 1. Okay, so you can see that for the diagonal, it will always be 0. Okay, because the connection the diagonal is simply the connection of the NOC itself. Okay, so usually in the graph there will be no self edge. Okay, so usually it will be 0, the diagonal. Okay, so for the adjacency list, okay, so it's simply will be the pairs. Okay, will be the pairs of the edges. So say for example for A, when we look at NOC A here, so we have AB, so we have the AB pair, and then AD, and then AD pair. And then similarly, we have BA. Okay, so BA is here, and then BD is here, etc. Okay, so this is the adjacency list. So how about weighted graph? So if it is a weighted graph, okay, like this, for the edges, we have the weights. We have the weights here. Okay, then the adjacency matrix will be represented similarly. Still, it will still be an n times n matrix, but then the value, okay, so that it simply means, okay, you put the value of the edges into the matrix. Okay, and then for the adjacency list, so for the adjacency list, you simply put the value, the number of the weights, okay, into the vector. Okay, so that means now the vector will be the nodes, okay, plus the weights of the edge. Okay, so this is the adjacency list if it is a weighted matrix. Okay, so how about when we go on to study the social network? Again, we need to understand the matrix. So what are the matrix that will be used to study social network? There are actually 3 matrices. Okay, so the neighborhood matrix, the centrality matrix, and the collective influence algorithm. So for the neighborhood matrix, okay, for the neighborhood matrix is we are interested to know, okay, so how will one of the nodes in the network be influenced by its neighbors? Okay, so that's why we call the neighbor matrix. Okay, so and as I mentioned before, we are more interested in studying the first order neighbor. Okay, we usually want to understand more, okay, those one-hop neighbors. So there are a number of matrices, okay, that would be used to measure neighbor. Okay, so we are going to go through each of these, okay, later today. And then the centrality matrix. So the centrality matrix, basically it is used to quantify, okay, so how important a node is within the network. Okay, so again, there will be a number of matrix that we can use to understand. Okay, so how important a particular node is within the social network. And finally, is the collective influence. Okay, so the collective influence. Okay, so basically we are trying to study the whole network. Okay, and then when we study the whole network, we are trying to know. Okay, so how the every node in the network would be influenced, okay, by the other floating node within the network. Okay, so this is the collective influence. So there are a number of algorithms for studying collective influence: the PageRank, okay, the Gibbs sampling, etc. Okay, but given the length of the course, okay, so we are going to focus on PageRank, which I'm going to introduce it later today. PageRank actually is an algorithm being used by the Google search engine. Okay. Okay, so first of all, let's talk about the neighbor matrix. Okay, so for the neighbor matrix, there are a number of matrix that we could make use. Okay, so the first one is the degree. So degree would be simply the number of connections, okay, to a particular node. Okay, and then we have the triangles. So triangles simply means you're counting the number of triangles, in the network. Okay, because triangles is what we call a fully connected graph. Okay, because 3 nodes, okay, 3 edges are the fully connected graph. Okay, so that means, okay, so why is triangles important? Because the triangles would be a fully connected graph. So that means, so that 3 nodes would be very closely associated with each other. Okay, so that's why triangles is an important concept. And the other thing is about density. So density is actually we are trying to check. Okay, so how the extent of what should I say? Okay, so for a fully connected graph, okay, so they are highly associated. Okay, so in a way that is density. Okay, so when density equals to 1, okay, so all the nodes, they are fully connected together. Okay, so they are highly associated with each other. So in a way, but in most of the social network, usually they will not be fully connected with each other. Okay, so in a way, density will be measuring. Okay, so how close they are to, how close they are being connected or associated with each other in the graph. And then for relational neighbor and probabilistic relational neighbor, so these are actually measuring the probability. Okay, so the probability of a node of being a fraudulent node or a non-fraudulent node. Okay, so given you know the conditions of the neighbors. Okay, so this is an overview of the example. I'm going to talk about each later, but just simply give you an overview. So say, for example, in this graph, so 0 means non-fraudulent or what we call legitimate node. Okay, so the 1 here, or the red one here, okay, so are the fraudulent node. Okay, so usually we will study the properties, okay, or the matrix of each of the node. Okay, actually each of the node. Okay, we are going to study each of the node, okay, in the network. So say, for example, in this case, we only look at node A. Okay, so for node A, so the degree is very easy to understand. So the degree of node A, the total degree, okay, will be, okay, so we want to know how many nodes are being connected to node A. So that means 1, okay, 2, 3, 4. Actually, it is very simple counting. So the degree of A is 4. But as I said, okay, because we are studying some fraudulent network, okay, so we want to separate the degree into fraudulent degree, okay, and legitimate degree. Okay, so in this case for node A, so the fraudulent degree will be 1, 2, and 3. Okay, and then the legitimate degree will be 1. Okay, so that is how you interpret the degree. So for the triangles, okay, for the triangles here, you look at the whole graph, the whole network. Okay, so there are 6 triangles. Okay, 1, 2, 3, 4, 5, 6. Okay, 6 triangles. So for density, I'm going to explain the formula later. And again, for the relational neighborhood, okay, I'm going to explain the formula later. So we are going to use this sample network, okay, so throughout this morning. So that's why now you can create a table like this, okay, because in this graph, we have node A, B, C, D up to T, okay, in the network, okay. And then we can have the total number of degree for each of the node, okay. And then we have the fraudulent degree, and then we have the legitimate degree. Okay, so as I mentioned in the previous slide, so you can see, again, when we look at node A, the total degree of node A actually is highest. Okay, so what does this mean? What does this mean? So A has the highest total degree. Okay. Okay, so the degree is simply, you know, how many neighbors the node has. Okay, so that means, okay, so if, say, for example, if this is a friendship network, okay, so it simply means that A got the most friends, okay, when compared with all the others in the network, okay, the most number of friends, okay, in the network. But then, what we are more interested, okay, would be the fraudulent degree, okay, because we are trying to study fraud, right? So we are more interested in how many fraudulent friends, okay, say, for example, if this is a friendship network, how many fraudulent friends, okay, so that each person got in this network. Then we found that actually G. So G is being associated with the most number of fraudulent nodes here. Okay, so you can see that G actually, although G got 4, okay, so total degree is 4, but the fraudulent degree actually is 3. Okay, so G is being associated with 3 fraudulent knocks here. Okay, and there is in-out degree. Okay, but because this is not a directed graph, so we don't have the in-out degree. But if this is a directed graph, then we would also have the in-out degree. Okay, in the table. So some very interesting observation about degree, the distribution of degree. Okay, so what does this graph indicate? Okay, so this is the number of, the x-axis actually is the number of people. Okay, so this is the y-axis is the degree. Okay, so what does this, how to interpret this distribution? So it simply means that we got only very few people with a very high degree. Okay, so most of the people here will have a very low degree. So what does this mean? Okay, so I'll give you an example. So say, for example, on the social media network, say, for example, on Instagram. Okay, so for those celebrities, okay, they might have over 1 million followers. Okay, so that is the degree, okay, of the celebrities' IG accounts. Okay, but then for some ordinary people, so like me, so for example, okay, so my IG account may only got, you know, say less than 100 followers, for example. Okay, so that is what this means. So it simply means that in real life, so usually we only very few people will got a very high degree. Most of the ordinary people here, okay, will have very low degree. Okay, so that is, you know, one of the you know, or the characteristics, okay, in real life or on the social network, okay, about degree distribution. So the other concept that I would like to introduce is a K-regular graph. Okay, so K-regular graph simply means the degree for all the nodes are constants. Okay, so say, for example, this one is a 4 regular graph. So it simply means that each node will have 4 degrees. Okay, so that means each of the nodes will be connected to 4 other nodes in the network. Okay, so this is a regular graph. Although I cannot think of any real life example that, you know, you might have a regular graph. Okay, but anyway, so these are, you know, some of the interesting observations for the degree. So the other properties is about the other neighbor matrix for the network is triangles. Okay, so triangles is simply defined by any subgraph in the network with 3 nodes. Okay, and then they are all connected. Okay, so this is so for triangles, actually this is a what we call a fully connected graph. Okay, so and also as I mentioned earlier, why we are interested in triangles, because they are fully connected. Okay, so that means so these 3 persons, they are very closely associated with each other. Okay, so usually there are 3 types of triangles. The fraudulent triangles. So fraudulent triangles simply means all 3 nodes are fraudsters. The legitimate triangle, so all 3 nodes are legitimate nodes. And semi-fraud means that, you know, so partially some of them are legitimate and then some of them are fraudulent. Okay, so again, just some examples. So this is a fraudulent triangle. So this is a legitimate triangle. Okay, and then we have here the 2 semi-fraud triangles here. Okay, so again, so that means we can put these back, okay, into a table like this. Okay, so what this means is that, so this is fraudulent triangle, legitimate triangle, and semi-fraud triangle. So again, so say for example, we look at this fraudulent triangle, okay, and then this is a non-fraudulent triangle, and then these are the semi-fraudulent triangles. So actually, because we only got 4 triangles here, so you can see, say for example, when we look at the nook here, look out here, so nook out here, so it doesn't belong to any triangle. So that's why all the values are 0. Okay, actually, it is very easy to understand. So for nook A here, so nook A is here. Okay, so this is nook A. So for nook A here, so it belongs to one semi-fraud triangle. So that's why this has the value 1. Okay, okay. And then these 2 values with 0, so the total is 1. Okay, and then say for example, if we look at nook D here, so D belongs to 2 triangles. Okay, so you can see that for D, it belongs both to a fraudulent triangle and then also to a semi-fraud triangle. Okay, so that's why the total is 2. Okay, actually very easy to understand. Okay, so that's why you can put all the numbers here. Okay, so this is the examples. Okay. And then another matrix is density. So as I measure, so density is used to measure the extent, okay, so to which the nodes in the network are connected to each other, or how they are associated or closely linked to each other. Okay, so it is measured by counting the number of observed edges. Okay, so it actually, this is a ratio. So this is the ratio of the number of the observed edges to the maximum possible number of edges in the graph. Okay, so that's why this is the this is the ratio or the proportion. So M here is the observed number of edges. Okay, so this is the maximum possible number of edges. So N is the total number of nodes. So this is actually a simple permutation. Okay, so this is a simple permutation. So after simplifying the formula, okay, so the permutation here equals to this, okay, this formula. Okay, so after simplifying the whole formula, we got the formula like this. So density will be equals to 2m over, okay, n times n minus n. Okay, so this is the formula to calculate density. So given the formula, so again, so when we look at the social network here, okay, when we look at the social network here, okay, then we can tableize, okay, we can tableize all the values into the, we can put all the density value into the table. Okay, so let's look at the nook G here, nook G here. Okay, so when we look at nook G, so what is n? Okay, so let's go back here. So what is n? So n is the total number of nodes, right? So n is the total number of nodes. Okay, so when we look at nook G, okay, so when we look at nook G, so n, okay, we want to count n. So n, so that is 1, 2, 3, 4, and then including nook G. So that's why we have 5. Okay, we have 5 here. Okay, then we look at M. Okay, so what is M? So M is the maximum possible number of edges in the graph. Okay, right? So that's why the maximum number of edges, okay, if we got 5 nodes, okay, will be 10. Okay, so this is actually a permutation. Okay, so then what is so sorry, n is the total number of nodes. M is the M here. M is the observed edges. Okay, but then we need to calculate the maximum number of edges if we got 5 nodes. Okay, so this is what it means. Okay, if we got 5 nodes, So the maximum number of possible number of edges will be 10. Okay. So for the value m here, okay, so we need to count the observed number of edges. So again, so that means 1, 2. Okay, so you also need to count this one, 3. Okay, and then 4, 5, 6. So that's why you got 6 here. So that's why you got 6 here. Okay, so that's why the density, okay, because the density is the observed number of edges over the maximum possible number of edges. Okay, so that's why it is 6 over 10. Okay, so that's why it is 0.6. Okay, okay, so that is how you calculate the density. So in this graph, okay, so you can see, so actually in this graph, if we look at the density value, the highest density value actually is for F here. Okay, so the highest density value is F. Okay, which is a 0. Sorry, the highest possible value is 1. Actually, is E. Okay, is E. Okay, is E. Okay, another one is P. Okay, is P. Okay, so why? Because for the triangle in the network, the density is usually equals to 1. Okay, density is usually equals to 1. Okay, so you can see that because E here, okay, so E just only belongs to this triangle. Okay, so that's why the density is 1. Okay, but why is the triangle in the network, the density is always equals to 1? Why? Why is the density is always equals to 1 for triangles? Okay, so let's go back to look at the formula. Okay, so the formula or the definition of density here, okay, is the number of observed edges over the maximum possible number of edges in the graph, right? Okay, so think about it. If this is a triangle, this is already a fully connected graph, right? Okay, so the observed number of edges will always be 3 here, right? And the maximum possible number of edges in the graph also will always be 3. Okay, because we think about it, for a triangle, you can only have 3 edges. Okay, so that's why 3 over 3 is 1. So that's why for triangles in the network, the density will always be equals to 1. Okay, so you can see that there are a number of triangles. Okay, if it is only connected to one triangle, then the density is 1. Okay, okay, and then for the egonet, okay, with degree 1, okay, the density is always equals to 1. So what is an egonet? Okay, egonet with degree 1, what does this mean? So this is actually an example of an egonet. Okay, if you remember, so egonet simply means we are only looking at one hop. Okay, and then with degree equals to 1, okay, so that means the node is only connected to one other node in the network. Okay, so R actually is an egonet with degree 1. Okay, so of course the density will always be equals to 1. Okay, so that means you only got 2 nodes. Okay, and the observed number of edges will always be equals to the maximum possible number of edges. Okay, which is also 1. Okay, so 1 over 1 is 1. Okay, so that's why for egonet with degree 1, the density is always equals to 1. So that's why you can see the maximum number. Okay, there are a number of nodes with 1 here. Okay, but how are we going to interpret the network? I think more important is you look at the apart from purely looking at the density. Okay, purely looking at the density value. So what we want to look out is, okay, so a combination of matrix. So in this case, you can see, okay, I highlight here. Okay, so we are not looking at the NOx with a high density value, we are also looking at whether the NOx also got a high fraudulent degree. Okay, so let's go back to look at the degree here. So you can see from here, the NOx with the highest fraudulent degree actually is NOx G. Okay, it's NOx G here. Then we go back and look at the density. Okay, so although G, okay, the density value of G is not highest. Okay, but I think if we compare G, okay, with the other NOx, okay, with the other legitimate NOx, okay, so I would say with the other legitimate NOx, so actually the density of G is also high. Okay, of course, these are fraudulent NOx, okay, EFG, sorry, EF and I think this is H, okay. So for these, okay, they also got very high density, okay. But what we are interested, as I said, are actually those legitimate NOx. And that also has a high fraudulent degree. Okay, so that means usually I will be looking at the NOx connected to the fraudulent NOx. So in here, you can see G got a high fraudulent degree, okay, the highest fraudulent degree, and also a high density. So we can infer that. So this is not exactly a conclusion. So this is an inference. Okay, we can infer that. So for NOx G, it will have a higher probability to commit fraud in the future. Okay, so that means, okay, so over this network, okay, so I will monitor G, okay, in the future for any potential criminal acts or any fraudulent acts, actions in the future. So I think that is one of the way to interpret the social network matrix. Okay, so I think let's take a break here. Let's take a very quick short break here. Before we go on to discuss the remaining matrix, let's take a 10 minutes break. Okay, so let's resume at around 10 before, maybe just before 10:30, 10:30. Okay, so let's take a break here. Okay, so let's continue. Okay, so we are still talking about the neighborhood matrix. So the remaining neighbor matrix include the relational neighborhood. So what is relational neighborhood? So basically, you can treat it like a classifier. So in a way, it is trying to calculate the probability of a node. Okay, so being a fraudulent node or non-fraudulent node. Okay, so given that it is connected to the other fraudulent and non-fraudulent node. So basically, this is a what we call the posterior class probability. So this is a posterior class probability of node n. Okay, belonging to, C is the class, so C can be 0 or 1. Okay, maybe you take 0 as legitimate and 1 as fraud. Okay, so this is simply counting, okay, the number of nodes. Okay, so that is being is neighbor, that is being a fraudulent node or non-fraudulent node. Okay, so I'll explain it using an example, which is easier to understand. So we want to understand, okay, so the probability of this question mark. Okay, so this is the node of interest. Okay, so the node of interest here. So first of all, we want to check the probability of this node. Okay, so being a fraudulent node. Okay, so the probability is simply equals to, so 1 over z. Z is the total number of nodes connected to this node. Okay, and then it is a simple counting. Okay, so we got only 2 fraudulent nodes. Okay, so that's why 1 plus 1. Okay, and then the probability of non-fraud, okay, will be counting the number of nodes that are non-fraud nodes. So that is 1 plus 1 plus 1. Okay, so that's why the probability of fraud of this node is 2 over 5. And then the probability of non-fraud of this node is 3 over 5. Okay, so I think this is quite easy to understand. So again, so that's why, okay, so we can calculate, okay, and we can fill in a table like this. Okay, so with all the nodes, so each of the node will have the probability of non-fraud and the probability of fraud. Okay, so in the network. So again, when we look at G as an example, so G here, okay, so the probability of non-fraud, okay, of node G, okay, so it will be 1 over 4. Okay, 4 because it is connected to 4 nodes. Okay, so that's why 1 over 4. So times 1 because only 1 non-fraudulent node. Then we have 0.25, and then the probability of fraud, okay, of G, so will be because it is connected to 3 fraudulent nodes. Okay, so that's why 1 plus 1 plus 1. Okay, so the probability is 0.75. Okay, so quite easy to understand. And again, when looking at the probability of fraud here, so you can see that for node G, actually the value is also quite high. Okay, although again, not the highest. The highest of probability of fraud is E. Okay, so where is E? E is here. Okay, but then because E is already a known fraudulent node, okay, so actually we are not interested in studying E. Okay, so again, as I said, we are more interested to study those non-fraudulent nodes. Okay, because we want to know whether these non-fraudulent nodes would be influenced by the other fraudulent node in the network. Okay, so again, so looking at the matrix, so we'll see that G, okay, the probability of G is also quite high. Okay, so again, we might need to monitor the actions of G, okay, in the network. So the other one is about probabilistic relational neighborhood. I think the idea is the same, okay, but now instead of only looking at whether the neighbor, okay, the one hope neighbor is fraudulent or not, we also take into consideration, okay, the probability of the neighbor the neighbor node being a fraudulent or non-fraudulent node. Okay, so let's again look at an example. So that means, okay, now we also take into consideration. So each of the node is not simply fraud or non-fraud. Okay, so each of the node also got the probability. Okay, so the probability of being fraud and the probability of being non-fraud. Okay, we also got the probability value of each node. Okay, so that means this time, so for example, when we look at the probability of fraud, okay, then we look at the probability of fraud of each of these, okay, one hop neighbor. Okay, so I think it's very easy to understand. So when we look at the probability of non-fraud, so this time again, we sum all the probability of non-fraud of the nodes in the network, okay, which are the one hop neighbor, okay, and then we got the value. Okay, then we got the value. Okay, so another concept of making use of the what we call the network characteristics in a way is we try to combine, okay, the what we call the network properties, okay, into some supervised learning model technique. So in this case, we are trying to make use of logistic regression. Okay, so say for example, you define some network characteristics here. So the mode link here. So the mode link here. So the mode link simply means, okay, so the most frequently occurring class of the neighbor. Okay, so let's take this example. Okay, let's take this example. So the mode link equals to non-fraud. Okay, because we got more non-fraud neighbor, okay, connected to this node. Okay, so that's why the mode link is non-fraud. Okay, and the other one is the count link. Actually, the count link, I think, is similar to degree. So actually, this is the degree. Okay, and of course, we divide it into fraud and non-fraud again. Okay, again, so this is the fraudulent degree. Okay, so this is the non-fraudulent degree. Okay, so in the graph, okay, so we got 3 non-fraud, so that's why it's 3. We got 2, so that's why this is 2. And then we can define something called a binary link. Okay, so the binary link, so it simply means that whether a particular class is present or not, okay, in its neighbor. Okay, so you can see that for this node, okay, because it is connected to both the fraudulent node and the non-fraudulent node. Okay, so that's why you got the one value for both here. So say, for example, if this node is connected to all non-fraudulent node, okay, then this binary fraud value will be 0. Okay, so this is what it means. So you can see, actually, in addition to the neighbor matrix that we just introduced, you can define some additional what we call the network characteristics, and then you insert it back into the original data sets. Okay, so this is actually, you will have something like this. So that means in the original data set, you can have what we call the intrinsic variables. So those intrinsic variables are the original attributes, okay, in the data sets. Okay, and then you can have some network variables. So the network variables will be, you can obtain these from the network matrix, okay, or you can define some new network characteristics. Okay, I think the caution here, okay, simply means that it doesn't mean, okay, because now you created some new network variables, okay, but it doesn't mean that all these network variables would be useful. Okay, so you need to be very careful. Okay, so as we mentioned before, you after inserting these network variables, you might still need to go through, okay, the EDA process again. Okay, so to make sure whether these variables are actually useful, okay, for the next step to build your supervised learning model. Okay, I think one very obvious selection criteria is to check, okay, so whether these variables, these new network variables, got any correlation with the target variables. Okay, so basically, if not, I think that you can drop the network variables. It simply means that these are actually not very useful. Okay, so so again, you can have write a table of something like this. Okay, so after defining you know, some new, okay, network characteristics that we have discussed before. So again, in this table, we can see that for G here, okay, because if we're simply looking the table, we would be more interested again in looking at those related to the fraud value, okay, to those values related to fraud, okay, and then we can see that for G, okay, the count, okay, so the count actually is the fraud degree, okay, got the highest fraud degree for G here, okay, so those are the network matrix. So let's go on to discuss the centrality matrix. Okay, so as I mentioned before earlier today, so the centrality matrix will be used to actually we try to use all these matrix and try to quantify. Okay, so how important is a particular node within the network? Okay, so these matrix would include the geodesic path. So the geodesic path actually is the shortest, it simply means the shortest path, okay, between two nodes in the network. So degree, the definition is the same as the neighbor matrix. And then we have the closeness. Okay, so the closeness, again, actually it is, we are talking about the distance. Okay, the distance of one node, okay, to all the other node. Okay, and then the betweenness. So betweenness means, you know, whether one particular node in the network, okay, is lying in between all the other nodes. So say for example, if that is an email network, okay, so you may want to know, okay, so whether the communications among all the others, okay, will be going through some particular persons, okay, so that is betweenness, okay, and finally is the graph theoretic center. So the graph theoretic center is defined by the node with the smallest maximum distance to all other nodes in the network. So what does this definition means? It simply means that, so the graph theoretic center will means that node is very central, okay, it's very central in the network, okay, so this is what this definition means. Okay, I'll give you examples later. So the geodesic path or the shortest path. So how are we going to calculate, okay, so the shortest path will be the minimum distance, okay, for one node to another node in the network. Okay, so I think that the key questions here is we also want to know, okay, so how would the fraudulent node how could it reach all the other nodes, okay, in the network? Okay, so we will make use of the Dijkstra's algorithm. So this is the details of the algorithm. I think I would explain it using example. Okay, but first of all, for the Dijkstra's algorithm, the first step here is you need to do an initialization. Okay, so that means now we look at node A here. Okay, node A here. Okay, first of all, we initialize a vector. So this is the vector of node A. So what does this mean? So this is the vector of node A. Okay, this is the initialized vector of node A. So it simply means A from A to A. Okay, from A to A, of course, this is 0. Okay, this is to itself. And then from A to B, okay, the second is B, and then A to C, okay, etc. Okay, so initially you want to initialize the vector. So all these are actually the distance. Okay, you initialize the distance from A to all the other nodes in the network using an infinity value. Okay, using an infinity value. So that is the initialization. Okay, so that is the initialization step. So again, this is the main loop of the Dijkstra's algorithm. I'm going to explain it using an example. It will be easier to understand. Okay, so what the algorithm does, okay, is something like this. Okay, so first of all, so you can see, so this initially, so this is the initialization. Okay, the initialization of vector A, okay, would be 0 and then infinity. Okay, so that means you can look at table here. Okay, then we perform step 1. Okay, step 1. So what is step 1? So step 1 is, first of all, we look at node A. Okay, we look at node A. So node A is directly connected to B, C, and D, right? So we only look at B, C, and D. Okay, so for A to B, okay, the distance is 2. Okay, so you fill in 2 here. So it simply means that from A to B, distance is 2. So 2 is smaller than the initial value infinity, right? So that means you will take 2 as the value. Again, for A to C, we have the value 5 here. Okay, so 5 is smaller than infinity. Okay, so that's why you will take 5 here. And again, for A to D, mind you, so this is a directed graph. Okay, so you can see A can go to D like this. Okay, and D can go to A. So D to A will be 1. Okay, but A to D would be 4. Okay, so that's why you take 4 here. Okay, so 4 is smaller than infinity. So that's why you take 4 as the value here. So after step 1, so then step 1 is done. Okay, for node A. Okay, then now the vector becomes like this. Okay, 0, 2, 5, 4, infinity, infinity, infinity. Okay, now because now node A is done, okay, we look at node B here. Okay, so step 2, okay, we look at node B. So B cannot go back to node A. Okay, so that's why no updates for A to B. So A to B is still 2. But then we look at B. B can go to C, okay, with a distance of 2. Okay, so now B to C is 2. Okay, and A to B is 2. So that means 2 plus 2, which is equals to 4. 4 is smaller than the previous value 5. Okay, so we will take 4 as the distance between A to C. Okay, so that means for A to C, so A going to C can go like this. Okay, the distance is 5. But actually, if we want the shortest path, it will be A to B and B to C. Okay, can you see that? Okay, so actually, because A to B is 2, B to C is 2, which is 4. 4 is smaller than 5. So we will take 4 here. Okay, 4 here. And again, because we are looking at B here, okay, so B is connected to A, C, and then we now look at B is connected to E, okay, through this path, and the value is 7. Okay, so now we look at here, we put 7 here. And because A to B is 2, so that means A to E is 7 plus 2, which is 9. Okay, so that's why after the second step, you will have the vector updated like this. Okay, so this is the vector after step 2. Now we go on to step 3. Actually, the process is very similar. Okay, we look at step C. So again, C cannot go back to A. Okay, so that's why it is not updated. Okay, it is not updated. And then for C, C can go to D like this. Okay, so C go to D is 1. Okay, so that means 1 plus 4. 4 is this value. Okay, so 1 plus 4 is 5. So 5 is still larger than 4, so we will keep 4. Okay, and then for C, C can go to E and also can go to G. Okay, so again, for C go to G, for C go to E here, the value is 4. Okay, again, 4 plus 4. Okay, 4 plus 4 here is 8. Okay, so 8 is smaller than 9. So that's why we will take 8 here. Okay, so similarly for G. Okay, so G, the value of C to G is 3. So 3 plus 4 here is 7. So 7 smaller than infinity. We will take 7 here. So similarly, we go through all the network nodes, and then we will have the final vector here. So this will be the final vector value for A. Okay, so this will be the final vector value for A. Okay, going to all the nodes, the distance from A to all the nodes in the network, which is the shortest or which is the minimal distance. Okay, so this is how the Dijkstra's algorithm works. Okay, so after calculating A, so similarly you can, so in the network, actually you can create an adjacency matrix like this. Okay, so this is the adjacency matrix. So again, so this is A, okay, this is B, okay, etc. Okay, and then this is A, and then this is B, okay, etc. Okay, so that's why again you can see the diagonal will be 0. Okay, for this adjacency matrix, the diagonal value will be 0. Okay, so this is how you calculate the shortest path. Okay, but I think that there is a note here. Okay, so the Dijkstra's algorithm, okay, actually it simply means it is not applicable if you got some negative value for the edge weights. Okay, because it will counteract the results. Okay, so we assume, okay, all the weights are positive. Okay, and then what is the graph theoretic center? So if you remember, the graph theoretic center will be those nodes with the smallest maximum distance to all nodes. Okay, so what does this mean? So that means, okay, when we look at this adjacency matrix, okay, so first of all, we check the maximum distance from node A, okay, to all the other nodes is 13. So the maximum distance for node B going to all the other nodes is 11, etc. We check all the nodes. So among all these nodes, actually for E and G, okay, the maximal distance, okay, is smallest, okay, among all the nodes. Okay, so that means E and G here. So these two nodes are what we call the graph theoretic center. Okay, so that means these two are actually most central in the node. Okay, so can you understand why? Because these two nodes, okay, because they got the smallest, okay, actually the smallest distance in a way, okay, the smallest distance to all the other nodes. So in a way, okay, so that's why these two are what we call the most central, okay, in the network. Or you can interpret that in a way they are most important in the network. Okay, so that is the interpretation of the graph theoretic center. So for the average path length, okay, so the average path length of this graph is 4.9. Okay, so very simple calculation. You just take the mean. Okay, you just take the mean of the adjacency matrix without counting the diagonal. Okay, because the diagonal, will always be 0. Okay, so that is how you calculate the average path length. Okay, so that is a geodesic path. And I think there is also some other concepts here, okay, because sometimes you want to check, okay, so how many hops, okay, will lead to the connection to a fraudulent node, okay, so that's why, okay, so we sometimes we in addition to looking at one hop, okay, we will also look at some what we call the two hop path. Okay, so give you some example here is that, okay, so for A to D, okay, so this is one hop, okay, A to D is one hop, but actually A can also go through B and to D. Okay, so this is a two hop path. Okay, so this is two hop path. And again, so for B, okay, going to D, there is one hop here. It can also go through A, okay, and then to D. Okay, this is also a two hop path. I think the final example is a more complicated one. Actually, it is going to itself. Okay, if we want to create a two hop path, okay, so this is a two hop path, two hop. Okay, so two hop. Okay, it simply means the connection to itself. Okay, counting twice. Okay. Then we can have something like this. Okay, so what does these numbers represent? Okay, actually it means, okay, this is the geodesic path to the fraudulent nodes. Okay, so we are simply counting the length, okay, the minimum distance from one node, okay, to the fraudulent nodes in the network. Okay, the shortest path. Okay, so that's why you got these three. Okay, these three values. So again, as I said, so basically we can have one hop path, two hop path, and three hop path. Okay, so looking at this network again, you can see that actually for graph G, for the node G here, okay, so actually when we look at one hop, two hop, or three hop, okay, to the fraudulent node, okay, so remember we are looking at the distance to the fraudulent node, okay, so basically G, okay, got the highest number. Okay, got the highest number. So that's why again, so I would say I will monitor G, okay, for any potential fraudulent acts, okay, in the network. So in a way, you can see all the matrix are very consistent. Okay, all the matrix are actually very consistent. Okay, when we talk about the influence of the fraudulent node to node G. Okay, but then there is also another point that we would like to note in the network here, because now we are talking about centrality. Okay, so in this network, so actually node A is the graph theoretic center. So node A is the graph theoretic center. So that means, so node A is most influential, okay, or most central in the network. Okay, so from the fraud prevention point of view, so that means, okay, so we will also look out or monitor A, okay, because A got the highest influence in the network. Okay, so that means in case when A is being contaminated, okay, so that means it will influence all the other nodes very quickly in the network. Okay, so that's why we will also look out for A. Okay, so from the centrality matrix point of view. So the other measures is about closeness. Okay, so that means how close, okay, one node is to all the other nodes in the network. Okay, so basically before we measure to talk about the matrix of closeness, okay, so actually we calculate the mean geodesic distance of the node. Okay, so because the closeness is simply the inverse of this value actually. So this formula is very simple to understand. So this is actually taking the mean, okay, of the geodesic distance, okay, of a particular vertex. Okay. So for the closeness centrality, So the closeness centrality is trying to measure the mean distance from one node to each other in the network. So this is, as I mentioned earlier, it is the inverse of the farness measure. Okay, so it is simply 1 over. It is simply 1 over this value. Okay, so that's why you got the -1 here. Okay, so this is the closeness connectivity, closeness centrality. So you can note that, so the higher the closeness value, again, because we are measuring the centrality. Okay, so that means the higher the value, okay, so again, that means the more central the node is within the network. Okay, so again, I think that because we are taking the inverse value here, so I think that this simply means that you also need to look at the decimals. Okay, so do not just round the numbers. Okay, so say for example, let's look at this example. So you can see, first of all, you calculate the farthest the value. Okay, so the farthest value is the mean geodesic path at the mean geodesic distance. Okay, and then this is simply 1 over this value. Okay, 1 over this value. So in this graph, you can see for node A, okay, node A got the highest centrality value. Okay, and then you can see R and S here. Okay, they got the lowest value. So when you look at the graph, so actually R and S is, further away from all the other nodes, okay, in the network. So again, you can see the result is very consistent, because previously we said that node A is actually the graph theoretic center. Okay, so and again, for the closeness measure A, for node A, you also got the highest value. Okay, so the other measure about centrality is betweenness. So as I said before, so betweenness would be something like this. Okay, so we want to measure, okay, the extent to which, one of the nodes within the network is lying in between all the other nodes. Okay, so that means for all the other nodes to communicate, say for example, this group of nodes to communicate with these two, okay, they might need to go through this node. Okay, so this is the betweenness. Okay, so the betweenness centrality measure, okay, will be calculated by this formula. So this is a summation. Okay, so this is summation. So it simply means, okay, for 2 nodes, okay, J and K. Okay, so we first of all, so this is simply the shortest path. Okay, the number of shortest path between J and K. Okay, and then for this one, because we are trying to check, okay, the influence of node I actually. So it means the number of shortest path for node J and node K going through I. Okay, so this is what it means. Okay, so and then you calculate the ratio. So again, for the betweenness, okay, we can get a table like this. Okay, we can get a table like this, and again, you can see node A got the highest betweenness value. So this again is very consistent, right, with the previous centrality measure that we got for node A. Okay. So finally, for the network analytics, okay, so we talk about the neighborhood, we talk about the centrality. So finally, we are going to talk about the collective inference. Okay, so what is collective inference? So collective inference, okay, it simply means that, okay, we are trying to infer, okay, the probabilities, okay, of one particular node of being a fraudulent node. Okay, so actually the idea is you're trying to infer for each of the node within the network, okay, the probabilities of that node being a fraudulent node, okay, based on, okay, the influence of all the all the other nodes within the network. Okay. Of course, the rationale behind is, I think it is the same rationale or same assumption, okay, that we have discussed in the very beginning of this lecture, is that we assume that every other nodes, okay, will be mutually affecting each other, okay, within the network, okay. And for collective inference, okay, because previously when we talked about the neighbor matrix and the centrality matrix, okay, for the centrality matrix, we are looking at the whole network, okay, and again, I think for the collective inference, again, we are looking from the whole network, okay, to check the influence from all the other nodes to one node, okay, to one of the nodes. Okay, so as I mentioned, we are going to discuss the PageRank algorithm. So the PageRank algorithm is actually being introduced by back in 1999. Wow, it's over 20 years, okay? So, but anyway, I think that this is still a very popular algorithm, okay? It is being used by the Google search engine, okay, to rank the web pages, okay? So how it works, okay, how it works. So the idea is like this, okay? So what is PageRank? So PageRank is simply the probability, okay, the probability of one person, okay, visiting a particular web page. So take the example here, okay, take the example here, okay. So say for example, we have a web page A. So say for example, this web page A is Hong Kong U's web page, okay, that is www.hku.hk. Okay, so you want to calculate the PageRank. Okay, so that means you want to calculate the probability of people visiting Hong Kong U's web page. Okay, so the idea is like this. Okay, so you got some other web pages, so B, C, and D. So say for example, B is the web page of CS departments. Okay, so say for example, CS department may have a hyperlink, okay, pointing to 5 other external web pages, and one of the hyperlink is pointing back, okay, is pointing to Hong Kong U's web page, say for example. So first of all, okay, so the idea is, okay, if someone is visiting, say for example, you are looking at Hong Kong U, you're looking at CS department's web page. Okay, so the probability of you clicking or visiting Hong Kong U's web page will be 1/5. Okay, why? Because on the CS web page, there are 5 external links. Okay, there are 5 external links. Okay, so that's why the probability, okay, of you visiting CS web page, okay, and also going to visit Hong Kong U's web page will be 1/5. Okay, a very simple probability. Okay, and similarly, say for example, there is also another web page C. Okay, and this web page got 3 external links. Okay, and one is pointing to this web page A. Okay, so the probability of the person visiting web page C, okay, also visiting web page A will be 1/3. Okay, so similarly, if there is another web page D, okay, that has 2 hyperlink, okay, 2 external hyperlink. Okay, so for the person visiting this web page, okay, also visiting web page A will be 1/2. Okay, very simple probability. So that is the idea of PageRank. Okay, so the collective inference. So the collective inference, okay, so that means, okay, so we are calculating the summation of all these probabilities, okay, all these probabilities. So that is the idea. So that is the idea. Okay. So that means we will have a formula like this. Okay. We have a formula like this. So it simply means that, so the page rank of A, okay, A is one particular web page. So the page rank of A will be the probability. So this is the probability, okay, of one person following the link, okay, following the hyperlink on some other web pages. Okay, so this is actually, okay, so this is actually, okay, so this is actually these probabilities. Okay, so these, so this part, okay, so this part is actually, I'm sorry, these probabilities. Okay, so this is, so page rank of A will be composed of two parts. So the first part, so this part is simply for those people, okay, following the web pages pointing to web page A. Okay, but we still got another probability. Okay, so the other probability is some person not following these, but simply, you know, randomly, and then they bump into the web page A. Okay, so that means so that's why the probability is 1 minus alpha. Okay, so alpha is the probability of people following the hyperlink of other web pages. So I is the other web pages. Okay, and then this part is the probability of some other people just randomly going to, okay, the web page A. Okay, and then this probability you need to times a what we call a restart value. Okay, restart value. Okay, of course to calculate the restart value is a bit, the algorithm is a bit complicated. Okay, so I'm not going to talk about it. But anyway, so there is a restart value of A. Okay, restart value of A. Okay, so you simply take it as the probability of, you know, someone just jumping randomly, okay, to the web page. So there is two parts, okay, of the PageRank algorithm for one website, okay, for one web page. So if we take the whole internet into consideration, so that means, so again, this is just rewriting the formula using vectors, okay, and matrix, okay. So the formula, the idea is the same. Okay, so this is the page rank. Okay, this is a page rank, or this is simply a vector. Okay, the vector containing all the page rank values. Okay, the vector containing all the page rank values of all the internet. So the idea is the same. So this is still the probability of some people following some other web pages, and this is again the probability of, you know, some random server jumping to a particular page. So the idea is still the same. Okay, but then because it is taking into consideration the whole internet, okay, not looking at one particular web page. Okay, so the next step is how are we going to adapt this PageRank algorithm for fraud detection in the social network. Okay, so the idea is, so actually we borrowed the idea from the PageRank algorithm. Okay, we borrowed the idea from the PageRank algorithm. So the rationale again, okay, is that we suppose, okay, if some fraudulent node, okay, so or non-fraudulent nodes, it will propagate its influence throughout the network. Okay, so I think that is the idea. So the question is how we are going to adapt this formula. Okay, adapt this formula. So you can see basically I think that the idea is the same. Okay, for the page rank, so that means for each of the node, okay, you will calculate the page rank. Okay, so this is actually representing the page rank, okay, of each node. Okay, but the question is how are you going to define the restart vector? Okay, so what would be the restart vector for the whole network? Okay, so in this case, So for the restart vector, okay, for the restart vector, I think there are two ways to do it. One of the very simple way is you use a normalization. Okay, you use a normalization because for the restart vector, so that means initially you normalize all the nodes. Okay, that is one of the way. The other way is because for the network, supposedly you know which node is the fraudulent node, which is not. So for the restart vector, you simply put 0 for those non-fraudulent node, and then for the fraudulent node, you put 1, the value 1, okay, into the fraudulent node. Then you will have the restart vector. Okay, so that is the actually that is the idea. Okay, so that means you can calculate the page rank, but you can see that there are 2 page rank value. Okay, the difference, okay, is only you are using which restart vector. Okay, so as I mentioned, so the page rank base simply means you reset the restart vector, okay, using the same value, or you use some normalization form, okay, to take it as base. Okay, the other one is you know about the fraud value of the node. Okay, so that's why you assign 0 or 1, okay, to all the nodes, okay, based on whether it is a fraudulent node. Okay, so that is the idea. So that's why you got 2 page rank value. But I would say that using the page rank, using the restart value, the restart factor, using the fraud might be more meaningful. Okay, so especially if you already know about, okay, so which of the nodes are fraudulent nodes already. Okay, so these are the page rank value. So again, you can see when we look at the page, actually the highest page rank value is node D. Okay, node D is here. But again, as I said, because usually we are not so interested in those nodes who are fraudulent nodes already. So those are already known to us. So we might not be very concerned, okay, about these. We are more concerned about all the other nodes, okay, that has a high fraudulent, that has a high page rank value, okay, but which are not which is a legitimate node. Okay, so that's why when we look at the fraudulent value at the page rank value of G, okay, actually it is again relatively high, okay, as compared to all the other non-fraudulent nodes, say for example A here. So A got the page rank which is 0.08 something, okay, and then for G, okay, the page rank value is actually higher. Okay, so although you can see that if we use the restart vector, if you use a uniform distribution, actually A got the highest page rank value. Okay, so can you see why? Okay, why A got the highest page rank value if we use the base? Any idea? Okay, so again, because we are using a uniform distribution as the base, okay, so that means we are assuming, so that means in a way we are not taking into consideration whether these are fraudulent or not. Okay, so if you remember when we talk about centrality, so actually A is most central in the network. Okay, so what is page rank? So page rank, we are talking about collective inference, right? Okay, so that means A would get the most influence from all the other nodes. Okay, because A is most central in the network. So that's why it will have the highest page rank value. Okay, if we take all the nodes as equal 1. Okay, so that's why. Okay, that's one of the reasons why A got the highest page rank value. Okay, but anyway, as I said, I think if we are interested in the fraud detection, and if we already know that some of these are the fraudulent nodes, I think using a restart value of fraud would be more meaningful, okay, for the subsequent interpretation. Okay, so you can see that there is some interpretation that I already put down here. Okay, so you can see that actually from the table, actually for the NOC DEF, so this fraud triangle, okay, so actually they got the highest page rank using fraud as the restart value, okay, in the table. But I would say that these are not very useful information, okay, because you already know that these are the fraudulent NOCs. Okay, of course they are influencing each other. Okay, because again we are talking about collective influence. Okay, so what we are interested in the non-fraudulent NOC. So usually we will look at those non-fraudulent NOC, or we call the legitimate NOC, also having a high page rank value. Okay, so you can see that for NOC G, so actually the page rank value of NOC G is even higher than NOC I. Okay, but NOC I is here. NOC I actually is a fraudulent NOC. Okay, okay, so that means NOC G is actually being highly, so I would say NOC G is being highly influenced, okay, by the fraudulent neighbors. Okay, so in this case, okay, so that is how you interpret the numbers, okay, here. Okay, so this is about the page rank algorithm. Okay, so again, I think let's take a 10 minutes break, and then we'll go through the last few slides after the break. So let's take a break. Please come back at 11:30. Okay, so let's continue with we only got a few slides. Okay, so I think it's similar to all the other classes. Okay, I think I would reserve, towards the end of the course, not towards the end of the course, towards the end of the lecture today. Okay, so I will also give you some general feedback about the assignments and the mini case study, because I still got quite a number of questions from the students. Okay, and the exam. Okay, so anyway, so let's continue. So basically, so finally, what we are going to talk about is a featureization. So what is featureization? So featureization is simply means that, okay, so we are trying to map, okay, some of the what we call the network features, okay, so or the characteristics of the nodes within the network, okay, and put it back. So in a way, is to put it back, okay, so into the original data sets, okay, so that you could make use of them for further supervised learning model or unsupervised learning model, okay, so that means, okay, simply means that, okay, so now this is a sample network, okay, so for each of the node, then you can have, we have talked about all the neighbor matrix, the centrality matrix, the page rank, etc. You can have for each of the node, you can have, many values. So for these, so these are actually the attributes that you could make use of, okay, for the next step for you to build a classification model. Okay, so this is what the featureization means. So finally, for the graph, before we go on to discuss the case study, okay, so we have so previously, we mainly talk about the unipartite network. So what is unipartite network? It simply means that for within the network, okay, so all the nodes, they are of the same type. Okay, so that means all these nodes, okay, represent person, or all these nodes, okay, they represent a company, okay, a merchant, etc. Okay, so this is a unipartite network. So, and also the relationship between the nodes. Okay, so actually the meaning will be the same. Okay, the meaning will be the same. Okay, so this is the unipartite network. So for the affiliation or the bipartite network, okay, so it means that there are more than one type. Okay, there are more than one type of entities. Okay, representing nodes. Say for example, in this one, so you can have person. Okay, you have persons here, and then you can also have events. Okay, so the nodes can be person, or also can be events. Then that means for the edges, okay, okay, so you can have different meanings for the edges. Okay, you can also have different meanings for the edges. Okay, so say for example, for a person connecting to the event, so may mean that, okay, so this person is attending the event, etc. Okay, so this is the bipartite network. So for the representation of the bipartite network, actually is very similar for the previous one. Okay, but this time, instead of an n times n matrix, now this is a n times m matrix. Okay, so you can see that, say for example, for this matrix, for this adjacency matrix, now you can have the persons here, okay, and then you can have the events here. So 1 to 8 simply means the events, okay, and then the representation here is the same. Okay, so for if there is a relation, you put in 1. When there is no relation, you put in 0. Okay, so again, actually the idea is the same. Okay, so it's just the representation is a bit different. Okay. So lastly, okay, so the last few slides is about several case studies that make use of the social network matrix. Okay, so this one, actually this example doesn't really make use of the social network matrix, but I think this is an interesting one, so I also capture it here. So say, for example, this is about tax fraud. Okay, so you can see that, okay, every node here represents a person. Okay, represent a person, but you can see that the relationship could be different. Okay, the relation link could be different. Okay, and then you also have the person linking to, you know, some closed business here. Okay, closed business here. Okay, so in this graph, so we will say that this person, Susie, okay, so she got a direct relation with a person linking to a closed business. Okay, and then she got a two-hop. Okay, so this is a two-hop relation. Okay, to another person. Okay, also holding a closed business. Okay, and then we will say that, okay, you in this network, okay, there may be some alerts being triggered. Okay, but of course, quantitatively, so this is a qualitative. Okay, you look at the graph. Okay, but quantitatively, I would say that you still need to calculate. Okay, to use the network matrix. Okay, to confirm. Okay, your suspicions. Okay, or if you want to raise some alerts. Okay, so this is one example of the application of the social network. So the other one is about a system called GotYou, or a paper published by this group of researchers. Okay, so not a very new research. Okay, but anyway, so again, so you can see that, so this data set is about some credit card transaction, some credit card fraud. So they got for the data source, okay, they got what they call the factual data, okay, some historical data, and then some transaction data. So for the factual data and the historical data, they can extract, okay, some attributes, okay, some attributes from the data sets, and then they build the social network. Okay, they build a social network based on the transactional data and based on the historical data. Okay, and then they build the transaction at the social network. With the social network, they can derive some additional attributes. Okay, and then they define the direct network attributes and the indirect network attributes. So the direct network attributes are simply those social network matrix that we discussed before. Okay, and then the indirect network matrix, they make use of the PageRank algorithm. Okay, to calculate the PageRank value. So given all these attributes, okay, so that means they could, they can now, okay, so apply, okay, these attributes to build, okay, some model, okay, to predict any future crime. So this is a more detailed description, okay, about the data source. So the factual data will be, you know, I think some of the very basic information of the entities. Okay, so say for example the information of the credit card holder, okay, the information of the merchants, okay, etc. Okay, and the historical data, okay, will be what they say is the behavioral change of the entities. Okay, so that means whether there is any changes made to the demographics, okay, or the other information. So the transactional data, so will be the interactions. Okay, so that means whether a credit card holder is buying something, okay, from the merchants, okay, the transactions between the merchants, okay, etc. Okay. So the social network, okay, because they need to construct the social network, okay, to extract the network attributes. So the social network, okay, so will be mainly, so the nodes, okay, so the vertex of the network will be the people and the merchant, okay, the people and the merchant, okay, and then the edges, okay, will be the transactions, okay, between the people and the merchants. Okay, so of course the objective. Okay, so remember that every time we need to define the objective of the study. So the objective of this study is to check whether there is any fraudulent transaction. Okay, whether there is any fraudulent transaction. So this is the result. So that means initially they built 3 supervised learning model. Okay, the logistic regression, neural network, and random forest. So initially they make use of all the attributes. Okay, they make use of all the attributes. So this is, so we look at the AUC. Okay, we look at the AUC. Okay, so and then we found that actually random forest got the best results, best performance results, okay, among these 3 models. And then we further, okay, look at the random forest. Okay, so we look at the random forest making use of all variables, the random forest making use of the local variables, and the random forest making use of only the network variables. So you can see, so if we are taking all the variables, so the performance is the best. Okay, but I think when you look here, so it means that initially, so even though, okay, so if you are only making use of the local variables, so that means without the network variables, actually the performance is not that bad. Okay, but it means that with the addition of the network variables, okay, the model performance will increase. Okay, so of course, finally again, okay, so I would say that it will always be so that is what you need to think of. Okay, so say for example, initially you did not take into consideration the network variable. Okay, and then you got a performance like this. Okay, so say for example, because this is only the AUC. Okay, usually I will also look at the precision and recall. Okay, so say for example, if you want to further improve, okay, the model, okay, there are many ways to do it. Okay, of course, one of the way is you simply go back to do some parameter fine tuning, okay, of the model. That is one way. And then the other way to improve the model, it would be, something like this. Okay, you include some additional variables, okay, to see whether it will help you to improve the performance of the model. Okay, so this is also one of the way how to improve the model performance. So finally, so this is the last case study. So this case study is about money laundering. Okay, so I think this is a case study in Italy. In Italy, there is what we call the factoring company. Okay, they got something called the factoring company. So they got the database for the factoring company. I would explain what is the factoring company in the next slide. So anyway, so according to the Italian law, so this is the law in Italy. Okay, so actually the factoring company is a financial institute. Okay, so all the financial institute, they need to record transactions. Okay, that is amounts to at least, okay, this amount of euros. Okay, so I think one of the reasons is that they try to check whether there is any money laundering activities. Okay, because as we said before, okay, if you remember, okay, so for money laundering cases, okay, so usually people will break down a very huge amount, okay, to smaller amounts. Okay, and then also, they will try to anomalize, okay, for this central data set, because for the purpose of the research, they anomalize, okay, the collected data in the data set. So this is how it works, okay, in Italy. So when someone, so this is a seller, okay, they want to sell some kind of products or services, okay, to another one, okay. So the seller will produce an invoice, but the invoice is not directly passed to this person. So the invoice actually is being sold to the factor, okay, to the factor, okay? And then the factor will pay cash to buy the invoice, okay? And then the factor will take the invoice to debtor, and then the debtor will pay the invoice, will pay the money back, okay, to the factor. Okay, so this is how it works, okay? Okay, so again, you can see that this, I will show it again and again, okay? So that means every time you need to define the scope, okay? You start with the scope, okay, of the fraud data analysis. So first of all, so what is the scope of this? So the scope is we want to check the final step, okay? We want to check the final step. We want to check whether there is any suspicious payment, okay, in this final step, okay, whether anyone is trying to make some dirty money looks clean, okay. So we want, the objective is to check the transaction here, okay. So again, for the fraud scenario identification, you need to identify 3 components, okay. So you need to identify the committing person. So what are the entities involved, and what are the possible fraudulent actions? So in this case, the possible fraudulent actions will be you're making up some fake invoice, okay, or you overstate, okay, the amount, the invoice amount, okay, etc. So then you can get the permutation, okay, and then you create different fraud scenarios. So the preparation, okay, the preparation for the network analysis, okay. So in this case, okay, so the NOCs, okay, will be the seller and the debtor, okay, the seller and the debtors, okay. So they define 3 different types of networks, okay. So one is the transaction network. So the transaction network is between the seller and the debtor, okay, and then the economic sector. Okay, the economic sector network. So that means they want to study whether the NOCs, okay, they are of the they are related by the economic sector. So finally is the geographical area. So that means geographically whether they are near each other. Okay, so also, so in addition of constructing the networks, okay, they also create a new variable called missing ID. Okay, so that means they are checking the data set. Okay, so whether there is any information related to the owner, the representative, the counterpart, etc. Okay, so they create a new variable called the missing ID. But this missing ID is not used for handling missing data. Okay, so this is not used for data imputation, etc. So what is the purpose of creating missing ID in this case? Why do you think that we need to create a new variable called the missing ID? What is the purpose, or what is the rationale behind? Anyone want to make a guess? Any idea? Okay, so remember, so what this case is about. So this case is a money laundering case, right? It's a money laundering case. Okay, so what would you suspect? Okay, why do we need a missing ID? Okay, so that means, okay, so we might, okay, so as I said here, okay, actually we can have some companies, okay, that might be fake. Okay, that means that company might not be an existing company. So that's why you might have some missing information. Okay, remember all the NOCs actually is about the seller and the debtor. Okay, so that means, okay, if there is some missing information for the seller and the debtor, okay, so that may be, you know, some some questionable or suspicious activities or transactions. Okay, if you got some missing information, but then there is still some transactions among these. Okay, so we'll say that there is some suspicious activities. So that's why, okay, they also create a new variable, missing ID. Okay, so remember, so that means, okay, so again, when you are handling your data sets, okay, so don't limit yourself. So I think what I'm trying to point out or highlight here is that don't limit yourself to only those attributes available in the data sets. So sometimes you need to be more creative, I would say. Okay, by creative doesn't mean you create some or make up some data. Okay, by creative is you're trying to think about what would be useful. Okay, what would give you some additional insights. Okay, so actually that will be part of the feature engineering process usually. Okay, so before you go into build your model, I think just think more. Okay, think more about what would be something useful for you. Okay, anyway, let's go on. So this is the transaction network. So you can see that purely looking at the graph is not so easy for interpretation. Okay, right? But anyway, so this is they build three. So remember, actually they build three types of network: the transaction network, the economic sector network, and the geographical area network. So by that means, okay, so although we have a graph, so that means we can also calculate all the network matrix, right? So given the network matrix, so finally they are making use, okay, of these network matrix, okay, and the newly created control variable, and then they build the logit models are the logistic regression model. Okay, they build 4 models. Okay, they build 4 models. So this is a simplified table. Okay, so because initially there should be a number of network attributes. So this is about the geographical area network attributes. This is about the economic sector network attributes. So these two are about the transaction network attributes. Okay, so only a few network attributes are included here because I am only looking at those coefficients with significant value. Okay, for those without significant value, is not included here. Okay, but anyway, looking at the resultants table here. Okay, so these are the variables. Okay, up to the constants. Okay, if you remember logistic regression, we have the constants. Okay, so these are the variables. Okay, and then we have the R square. So that means we are using the R square to evaluate whether the model is good or not. Okay, so N is simply the number of records. Okay, so because I have not mentioned about AIC and BIC, you can just ignore these two. So for the R square, okay, the R square. So what is R square? So if you don't remember, I already included a slide here. So this is I think we talk about it when we talk about linear and logistic regression. Okay, so R square, okay, is the matrix, okay, for you to compare your model with the baseline. So if you remember, so this is actually the error term. You can take it as the error term. Is the error term of the model or the performance of your model. So this is the performance of the baseline. Okay, so in a way, for the R square is measuring how good, okay, is your model comparing to the baseline. So usually, for the R square, the higher the value means the better the model. Okay, okay. So Now let's look at model 1, 2, 3. So for model 1 here, so model 1 here, you can see it is taking into consideration only the missing ID. Okay, missing ID. Okay, so this is the performance. Okay, 0.129 for R square. Okay, and then for model 2, we take into consideration, okay, the network matrix from the geographic network and the economic network. So this is simply the in degree from the geographic network, and this is I think a network constraint. I think it is something defined by the author from the economic network. So if we are looking at these two networks, okay, without the missing ID, okay, but then you can see that for this model, the performance is better. Okay, the performance is better. Okay, and then for model 3, we take into consideration the network matrix from the transaction network. Okay, so this is the look at all the weighted all degree, okay, and the closeness. Okay, so these are also some of the network matrix. Okay, and then the performance is 0.167. Again, shows additional improvement than the previous model. So for the final model, model 4. So for model 4, we take into all the variables. Okay, we take into all the variables. And then we found that actually the performance is the best. Okay, it's 0.327. Okay, so that means, okay, if we take into consideration the newly created variable and all the network variables, all the network variables from the 3 networks, okay, actually the final model is the performance is the best one. Okay, so that's why we would take this model, okay, for to use in the future. Okay, and it also confirmed that, okay, so because initially, okay, we also want to test, okay, so whether SNA is the social network and analysis, okay, whether the social network matrix are useful. So in a way, it confirms that these matrix are useful. Okay, so this is how you interpret the results or analyze the results. Okay, so so this finally are some of the references. Okay, so again, I think for those who are very interested in having a textbook, okay, or want to look at textbooks, so these are the 2 main reference, okay, that I have used throughout the course. Okay, so I think this is the end for all the about the data analytics technique for this course. But again, so I just want to remind you, this is not the last lecture for the whole course. Okay, you still got the last lecture next week. Next week, Annie will come. Okay, I think next week will be the last lecture. Okay, for the whole course. So again, just a few feedback about assignment 1 and assignment 2. I know that I just want to say, so assignment 1, assignment 2, and the mini case study. Okay, we are all making use of the Enron data sets. Okay, so don't ask me again. Okay, are we using the same data set? Yes, we are using the same data sets all through. Okay, and again, assignment 2 is a follow-up of assignment 1. Okay, and then for your mini case study, it is a follow-up of assignment 2, assignment 1 plus assignment 2. Okay, so for those, say for example, if you don't have time, okay, or you think that assignment 1 and assignment 2, okay, you already put your best efforts already. You just put the results of assignment 1 and assignment 2 back to your mini case study. Okay, but remember, look through the mini case study. Okay, because apart from EDA, apart from building a model, okay, you still need to answer a number of questions. okay, and then to come up with the mini case study report. So the mini case study should be a whole report, okay, starting from EDA. Okay, no, not starting, should be starting from the objective. Okay, so that means if you have not yet defined the objective of your study for your assignment 1 and assignment 2, then for your mini case study, you have to define your objective. Okay, and then every step or, everything you write about the report should be consistent or answering, okay, or, reflecting or responding to the objective. Okay, so that means you cannot say objective 1, okay, and then what you're doing is totally unrelated to your objective. Okay, so that is what I'm trying to say. Okay, just make sure that your work is consistent. Okay, so that is one. The other thing about the mini case study is that, okay, so because for assignment 2, you are required to build 2 unsupervised learning model. Okay, but for the mini case study, because some of students ask me, they want to do more. Okay, ask me whether they could build 3 or 4 supervised learning model. I would say yes. Okay, so given that if you are very interested and you want to do more work, it's fine with me. Okay, because as I said, sometimes this is part of your learning process. Okay, and some other students also ask me, can they build then because I taught some other technique like the unsupervised learning model, I also talk about Benford's law, and today I talk about social network analysis. They also asked me whether they could use all these techniques for the mini case study. The answer is yes. Okay, so if you want to, okay, it's fine for your mini case study. You could do something completely different from your assignment 1 and assignment 2. Okay, but for me, okay, it will be easier for you, okay, if you just use the results of assignment 1 and assignment 2. Okay, because for me, one of the purpose of breaking down, in a way, actually, I'm breaking down the mini case study into smaller steps, because I want every one of you, I want to make sure every one of you can submit your mini case study reports. Okay, because in order to pass the course, the very minimal requirement for passing the course is you need to submit your coursework. Okay, because my experience in the past year, if you never submit any coursework, if you only come to take the exam, it is impossible for you to pass the whole course. You probably will fail. So I would say if you don't submit any coursework, you simply don't come to the exam. Okay, save your time. Okay, one last remark, okay, which I really don't understand, because every year in the past year we got students submitting incorrect assignments. So that means, okay, so when our TA tried to grade the assignment, they found students submitting assignments from another course, okay, which I totally understand. Every year we got at least 1 or 2 students. Okay, so anyway, so you are all master level students. Okay, so please double check your work. Okay, because in a way, it will be quite embarrassing for us, because we, but of course, usually I will ask the TAs, okay, go ask the student to resubmit again. Okay, but then of course, it will be a very late submission, okay, for the students. Okay, and we don't want that. Okay, so anyway, just be very careful. So about the exam, so I would only say that there are past papers. There are many past papers for this course, okay, in the Hong Kong U Library. Okay, so go take a look. Okay, so every year the format basically will be the same. Of course, the questions would be different, but the format will be the same. Okay, but don't ask me the answers for the exam questions. Okay, you work it out yourself. Okay, you work it out yourself. So or you can, discuss with your classmates, okay, about the answers. Since that would be an open book exam, okay, so of course the questions won't be very straightforward. Otherwise it will be too easy. Okay, but anyway, good luck. Okay, so and again, do come back next week, okay, for Annie's last lecture. Okay, so I think this is the last time I will be seeing you. The next time maybe you'll see me in the exam hall. Okay, so thank you.